Okay, guys. So we left off talking about Euler's method, right? So I did this example where we had this differential equation, this initial value problem. This is a first order differential equation. Trying to remind you guys, just for those who have forgotten, this is a first order differential equation because I'm just dealing with the first derivative here. And it's an initial value problem because we're using essentially one of our values at one of our t values at our function initial point to be able to approximate essentially this value, this solution at a particular location, and that gives us when we use that initial value, we're able to solve for the parameter c. All right, so we were talking about how can we approximate this this solution using another method, right, besides just kind of going through and finding a solution analytically, in this case, using integrating factor. And we use something called Euler's method. I'm going to erase this. This is out of the way. Should have erased this a little bit earlier. So this is a shower board that I got from Lowe's. It works pretty well as a dry erase board. It's not really a dry erase board, but you can use it as one. My wife came up with the idea of, told me about it. Well, at least one of her friends did, and she found out about it and told me. Okay. So let's get started. Let's talk about Euler's method. And so what we're going to do is we're going to actually approximate the solution using a Taylor series. And this is going to help us to extend to the idea of Taylor's method later. Approximate the solution. Y of t using a Taylor series. Okay. So remember we have y prime is equal to f of t and y, right? We talked about this before. And where we have y alpha equal to y naught, okay? Right, this is my initial value problem. Initial value problem. And what we can say is, okay, the Taylor series we're going to have y of t sub I plus 1, okay, y of t sub I plus 1. This is going to be equal to, well, what is y of t sub I plus 1? If we were to draw out a picture, I'm going to draw one over here. Let's kind of make this a little bit clearer. T sub I plus 1 is a node. I have to get a real eraser here soon. Okay. Suppose we have some kind of function. So we have t sub I. We have t sub I plus 1. Okay. They're apart. Let's suppose they're equally spaced by distance of h. Okay. So t sub I plus 1, when we come down to it, is really just t sub I plus h. Okay. So how do I get the t sub I plus 1? Just take t sub I, my first node, and add h to it. Okay. So what we're going to write is that y, so t sub I plus 1 is really y, so t sub I plus h. And we're going to expand this using Taylor series. And if you guys remember, with Taylor series, this is going to be equal to, we have here, y sub t sub I plus y prime of t sub I times h. All right, if you guys remember that, plus y double prime t sub I over 2 factorial times h squared plus da da da. Okay. This is our guy. And what we're going to do is we say, okay, we have y sub t sub I plus 1 is equal to all of this, right? And if I wanted to, I could expand this further. But I'm like, okay, so I'm just going to take the first two to be able to approximate my solution at y sub t sub I plus 1. So suppose I know y sub t sub I know what that value is, right? And I want to be able to approximate the next value, t sub I at t sub I plus 1, right? I want to be able to approximate this next value, right? I could use this entire Taylor series, or I could just take the first two terms of the Taylor series. I'm going to take these two terms as my approximation. Approximation, and I always misspell that. Okay, and the rest of it is going to be my error. So again, let's kind of recap. Y is my solution. Y is my solution. Suppose I know one part, I know one point of my solution, and I want to get to another point in my solution, right? What I'm going to do is I'm just going to use this Taylor series, just the first two terms of the Taylor series, to be able to approximate the next point of my solution, right? And so this is what we're going to write down. And this is actually Euler's method. This is what we want to talk about. And you kind of get the idea that to be able to extend this idea of the Taylor's method, right, is just kind of using more than just two terms of the Euler's, two terms of the Taylor series. But let me write it down here. Here's Euler's method. Euler's method. It's essentially just going to be y of t of I plus 1 is approximately equal to y of t sub I plus y prime of t sub I times h. Then I say, okay, with error given by what? Well, it's going to be given by these remaining terms of my Taylor series, right? And we've done this before. I can say my error is going to be, my absolute error is going to be less than or equal to f double prime, evaluated as z, times, divided by 2 factorial, times h squared, where h is the distance between t sub I and t sub I plus 1. We're going to assume that all the points are equally spaced, where z maximizes f double prime on the interval, wherever my interval is that we're looking at here. I just say on the interval from A to B, wherever that interval is that we're looking at for our initial value problem. Okay. So this is really Taylor series when it all comes down to it. Now the way people usually write it is this way. I mean, Euler's method. But the way people usually write it is this, and so let's put it down. It's a slightly different form as what you usually see it as. I'm going to do it here. Euler's method. The way that most people write it. They kind of write it in an iterative fashion, right? So instead of putting y of t of I plus 1, which is a mouthful, well, you say y sub n plus 1. So the next y value that we want of our solution is equal to, right? So we don't use the approximately, now, although that's what we're really doing. We're approximating what my next value of my solution is going to be. Is equal to y sub n, okay, which is this value, plus y prime. Now, I could put y prime sub n if I wanted to, but what is y prime equal to? If we look at it, y prime is equal to the function at evaluated at t and y, right? So what we're going to do is we're going to write this as f of t, which is going to make my t sub n, because I know that value, and then my y value, y sub n. Okay. So this is what we use. So it's going to be y sub n plus 1 equals y sub n plus f of t sub n, y sub n times h. Okay. And then we have our initial condition, which is going to be y of t sub 0, because t sub 0 is going to be our first node, is equal to y naught. This is it. This is our Euler's method. Again, error is still the same. Now, instead of, and so what do we call h? We call h is called the step size. Of our Euler's method. And so h will always be called the step size, but it's just the distance between my nodes, and we're assuming that all the nodes are equally spaced. So again, we're essentially just using, and I love that we keep coming back to this Taylor series idea, that we keep using this idea of this Taylor series, approximating a solution using my Taylor series. So my solution is approximately equal to the first two terms of my Taylor series, is what we're saying. And then I'm just using the fact that y prime is equal to f of t to y, which is this term right here. Okay, that's all we're doing. So let's see how well it compares with our previous one, with the solution that we got before. So remember what we had last time. So we have, if you guys remember, this is my solution to my my differential equation. We did this last time, and we got these values. And so let's put down the Euler's method for this particular differential equation. Gonna erase this. I gotta use the space more effectively. I'm not used to it yet, so I'm still having to figure out how to use the board. Okay. So let's go back to our previous example. So I'm going to approximate, in this case we have y prime equals y minus t squared plus 1, okay. Y of 0 is equal to 0.5 using Euler's method. Okay. Now notice that my f of t of y is equal to y minus t squared plus 1. Okay. That's what that's equal to. And then if we plug in, let's see, plug it in, right? So we have our Euler's method here. So our Euler's method is going to be y sub n plus 1 equals y sub n plus f. My f is this guy right here, so I'm going to have the quantity y sub n minus t sub n squared plus 1. And then lastly, we have y sub t sub 0. T sub 0 are 0 in this case. T sub 0 is 0, so we have y of 0 is equal to y naught, which is 0.5 here. Sometimes what you'll see is that people, instead of writing this, they'll put y sub 0. I'll do it this way. I have y sub 0, which is equal to y of 0 is equal to 0.5. Okay. Now, in this case, my t sub 0 does not have to be 0. It just so happens to be 0, which is the same thing as my initial point that I choose. It could be y sub 0 is equal to y sub 1 if my t value was 1 in my first one here. All right, hopefully that makes sense. All right, so let's compare. Let's compare this Euler's method, right, with the values that I have here. Now, what h do I have to choose to be able to compare these guys directly, right? Well, if you notice that these t values are 0.5 apart, right? 0.5, 0.5 apart. So I need to let my h be, oh, I forgot, where's my h? You like Dr. Wesley, you forgot your h. I need to multiply this thing by h. There we go. Okay. Now, if I want to compare these two guys, I need to use h of 0.5. So let's do that here. Use h equals 0.5, right? I could let h be smaller than 0.5. I can still compare them at those places. But let's use h equals 0.5. Okay. I'm going to have a table for all this method. I have n, I have t sub n, and I have y sub n. Okay, so my values. I'm going to use, let's say we want 0, 0.5, 1, 1.5, and 2. Okay, so my n is 0, 1, 2, 3, and 4. Okay. And I want to find my y sub n. So my y sub 0 is going to be 0.5. We already know that to be the case from what we started with. Okay, let's find y sub 1 and y sub 2, and then we'll just fill out the rest. Okay. Y sub 1 is equal to y sub 0, right, going by Euler's method, plus, here we have y sub 0 plus t sub 0 squared minus 1 times h, which is 0.5. Let's plug in what that is. Y sub 0 is 0.5 plus 0.5 plus 0 squared minus 1 times 0.5. Okay. If you work that out, you get 1.25. So y sub 1 is 1.25. So my approximating of the value of y at 0.5 is 1.25. If you look over here, that value was 1.43. Okay. Let's do y sub 2 real quick. Y sub 2 is equal to y sub 1 plus y sub 1 plus t sub 1 squared minus 1 times 0.5. Okay. So we plug in here, y sub 1 is 1.25. Plus the quantity 1.25 plus t sub 1 is 0.5. So 0.5 squared minus 1 times 0.5, my h. Plug that one in, you get 2.25. At least that's what I have. 2.25. Okay. And if you look at the value of our solution at 1, we get 2.64, not a great approximation, but at least it's in the same ballpark. If you do y sub 3 and y sub 4, this is what you get. Y sub 3, I get 3.375, and y sub 4, I get 4.4375, okay? So in this case, I can say, okay, y sub 2, my solution of the differential equation, okay, at 2 is approximately equal to 4.4375. Okay. Now, is that very close to the value of my actual solution? And the answer is no, not really, right? My actual solution is 5.3. Here I have 4.4375. That's pretty far off. What's the absolute error here? Let's look at the absolute error. Okay, absolute error. Let's get that out of the way. My absolute error is going to be equal to, is that 5.3 minus 4.4375, and this is my absolute error at y2, right? Between my actual solution and my approximation. and that is about 0.8625. Okay, I can get a better approximation by letting h become smaller. So the smaller I make the value of h, the better my approximation becomes. Let me see, and let me grab something real quick. Right? And we can analyze that error too. We'll look at that error later. But let's suppose h is equal to 0.2. Okay. H is equal to 0.2. I'm going to erase this real quick. This is also in the book, but I want to just show it to you guys on the paper, on the board. So suppose h is 0.2. Okay. So here we have before h equals 0.5. I still want to be able to approximate my solution at 2. Okay. Make a little table here. So n, t sub n, y sub n. Right. And the work will still be the same amount of work, but instead of using h of 0.5, we'll be using h of 0.2. So I have 0, 0. So when n is equal to 0, t sub n is 0, and y sub n is 0.5. Okay, and I want to use 0.2, so I have 0.2, 0.4, 0.8, 0.6, sorry, 0.8, 1, 1.2, 1.4, 1.6, 1.8, and then 2. Okay, a lot more values I have to work with. So n is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So 10 n's. And if you were to work this out, you would go through this process just like we did over here. You get this. For n equal to 1, our solution is 0.8. For n equal to 2, our solution is 1.152.